Hi. So we had last time we did an ed puzzle, we figured out that we could take the derivative, and that was like doing the slope. So we could figure out the speed from the position by taking the derivative of position to give us speed. We could find the acceleration by taking the derivative of velocity. Now we're going to go backwards, and that's a little harder. It's really the same thing, but it just looks worse. So we're going to talk about the antiderivative, otherwise known as an integral. So we're going to start by getting position from velocity. So if we have a function for velocity that depends on time, we know that the velocity is the derivative of position. So to find position, we work backwards, and that's the antiderivative. So we're finding the function that has as its derivative x of t. So let's go through an example. Suppose we have v is equal to 2t, and we want to find x. We know that dx dt is going to be 2t. So we're working backwards to figure out what x could be that we could take the derivative of that would give us 2t as an answer. As it turns out, t squared works. So if we have t squared and we take the derivative of that, that's going to give us 2t. So that is one possible answer. So now, it's not really that simple. That's not the whole story. T squared definitely works, but we also could add a 3 to that. So t squared plus 3. And if we took the derivative of t squared plus 3, the t squared becomes 2t, and the 3 just goes away. So it definitely works. And in fact, t squared plus any constant is going to work because that constant is just going to go away when you take the derivative. So when you're in calculus class and you're asked to find what's called an indefinite integral, so that's what this is an indefinite integral, you always want to stick a c on the answer because there could be a constant on there. Now, in principle, this isn't going to be much of an issue in physics. You're probably never going to write a C. And the reason is you're going to have initial conditions. They're going to tell you that when t is equal to 0, v is equal to some amount, or x is equal to some amount. And so you're going to know what value is going to go in for c. And this is one way that you could do it. So if we have v is equal to 2t, we know that x has to be 2t plus a constant. If we plug in 0 for t, then that means that we get 0 squared plus c is equal to 6. That means that c has to be equal to 6, which means that our function is going to be x is equal to t squared plus 6. So sometimes that's what's going to happen is you'll be asked to find that position, but you're going to know what x is at some value, and you can plug in for c. So it'll just be a number. So that'll be your initial position. So I want to give you a little bit more of the real story of what's going on here. This is all going to make sense, a lot more sense in the spring when you do integrals, but we're just going to get to the basic, like, this is how you do it thing. And then we'll do it more when we get to energy, and that'll be closer to November. But so here we go. Let's look at a VT graph like this one. So we have a VT graph. It's some weird function that's wavy and all sorts of stuff. We know that displacement is the area under the curve. So if we were to calculate, count up all the boxes underneath the curve, do base times height, or 1/2 base times height if they're triangles, we could figure out what that displacement is. So you'd calculate base times height, add them all up. If we make the rectangles super small, so they're little teeny tiny rectangles, so that it's a dt, so little teeny tiny segment of time on the x-axis, then the area of each rectangle would be the velocity at that time. So this right here. So that's going to be our base, or height, I guess, is how high up it goes. And then our base is going to be that dt. So it's going to be v of t dt. If we were to then count up all of those little v dt's, we could write that using the integral symbol. So that's what this little curvy S thingy is the integral symbol, which means that we're going to take the integral of v dt. So that means find all of the area. So add up all of these little rectangles for the entire thing. And in order to do that, integral means to find the antiderivative, so working backwards. And if this isn't making sense yet, that's okay, it will. So another way to look at that is algebraically. So if we have v of t is equal to dx dt, so the velocity is equal to the derivative of position with respect to time, we multiply both sides by dt, then dx is equal to v of t dt. To undo the d part of that, so the little bitty part, means that we do the integral. So if we integrate both sides, so we add up all the little d's, then x is the sum of all the little dx's. So if we integrate this side, that becomes x. So we just add up all the little d's, the dx's, that gives us x. And on the other side, that's integrating v dt. So that's another way to look at that. Okay, so now I want to talk about the definite integral. So sometimes you don't want an equation for x of t. Like that was one of the benefits of using derivatives instead of slope, is that we could find an expression for speed that worked for all times. So we didn't have to find the slope of each little t along the way. We could just derive the whole thing and get a function. Sometimes we want to do that, which is what we just did. So we figured out a function of our position vector as our position as a function of time from our speed. So we had a speed equation, then we could find a function of position. Sometimes we just want to know how far did it go, and that's what the definite integral is. So you could find an expression for x of t by taking the antiderivative and then subtracting whatever x was for the final time minus whatever x was for the initial time. So let's go back to our example. So if we want to find the displacement of a car moving with velocity v of t equals 2t from 1 second to 3 seconds, you can integrate. So you're finding the antiderivative of v dt. So that's 2t dt. This dt is not, it's just telling you what variable you're integrating over. So it's not something you have to worry about. It's only the stuff in front of that, the 2t, that matters. We already saw that that's equal to t squared plus a constant of some variety. So now if we figure out what x is at 1 second, plug it in, we get 1 plus c. If we figure it out at 3 seconds, that's 3 squared plus c, so 9 plus c. Then we can subtract the two of those to get the displacement. So we take 9 plus c minus 1 plus c equals 8, and the c's cancel out. So you don't have to worry about the c's anymore because they disappear. So there's a shorthand way to write this. We put in what are called limits of integration. So what we just did, a shorter way of writing that, is to write it this way. So our displacement is the integral of v dt, so v dt, from our initial time to our final time. So we just write it on the little s thingy, and that tells us that we're integrating from 1 to 3 seconds. Since the c's are going to cancel out anyway, we don't have to write c. Yay! So a shorthand way of writing this is once we figure out what the integral of 2t dt is, which we know is t squared, don't have to worry about the c, we can draw a line with a 3 and a 1. And what that means is evaluate the antiderivative t squared from 1 to 3 seconds. So we're doing exactly the same thing, except we can just ignore c. So t squared from 3 to 1, we take 3 squared minus 1 squared, and that's going to give us 8. So it's just a shortcut, shorthand way to write that. So this is really finding the area under the curve from one time to another. So it's giving a definite place where we want to find the area. So it's just going from this spot right here to this spot right here. So the short story, on your AP sheet, you have this. Isn't that awesome? So it tells you that if you want to take the integral of x of n dx, and again, this dx you don't do anything with. This just tells you that what you're integrating over is x. So this, you just ignore that x. So x to the n is the thing that you're finding the integral of. What you do is you raise the power by 1, because when you took the derivative, you lowered it by 1. And because when you took the derivative, you multiplied by the coefficient and the power, here you're going to divide by that n plus 1 power. And this doesn't work if n is equal to -1. So there's a different thing you do if n equals -1. And that's also on your AP sheet, but we won't get to that until later. And then for calculus class, don't forget there's a c added onto your answer. In physics, you're not going to have to worry about it, but I don't want you to get into the habit of not writing the c and then get in trouble in calculus. All right, so let's go through an example. My velocity is given by 3t squared minus 2t. How far do I travel between t equals 1 second and t equals 5 seconds? So I'm going to be integrating from my initial time to my final time of that velocity function, dt. So I'm going from 1 second to 5 seconds. My function is this, so 3t squared minus 2t, and then the dt just tells me that I'm integrating over time. So now I have to work backwards. I'm going to have a 3. I'm going to go t, I'm going to raise the power by 1, so it's t cubed, and I'm going to divide by that new raised power, so 3. So 3t cubed over 3. And I can always check to make sure that that's right by taking the derivative of this, and that should give me my original term. So if I take the derivative of 3t cubed over 3, that's going to give me 3t squared. So that's cool. And if I do the same thing for 2t, that's going to give me 2t raised the power by 1. That gives me 2t squared over 2. So then if I can simplify that, so I pick nice numbers so that the coefficients cancel, I get t cubed minus t squared evaluated from 1 to 5. That means that I'm going to plug 5s in first. So 5 cubed minus 5 squared. I'm going to subtract 1's plugged in. Now, oftentimes it starts from 0, which means that this term would be 0, but here it's 1 because I wanted to show you how it works. So then this is 1 cubed minus 1 squared. I can then simplify that, and I end up with 100 because minus 1 is just 0. So it's just 125 minus 25. That's going to give us 100. So how do you get velocity from acceleration? Since the area under the curve is velocity, you use the exact same process. So you would take the integral of velocity in order to get, the integral of acceleration in order to get velocity. So just like you do the area under the curve of acceleration to get velocity, it's the integral of acceleration to get velocity. So let's review the graphical relationships. So in order to get velocity, we take the slope of our position time graph. In order to get acceleration, we take the slope of our velocity graph. In order to get velocity, we take the area under the curve of velocity graph gives us displacement. Area under the curve of the acceleration graph gives us velocity. Everywhere you see a slope here, that's really a derivative. Everywhere you see an area under the curve, that's really integration. So in order to get velocity from x of t, we're going to take dx dt, so derivative. Acceleration is dv dt, so those are slopes. In order to get position, we're going to integrate velocity time. That's like area under the velocity time curve. And in order to get velocity, we're going to do integrate acceleration dt, and that's like the area under the acceleration curve. So, a summary. If acceleration is constant, it's often easier to use kinematic equations. So there they are. The equations result from taking the antiderivatives if there's a constant value of a. We'll do that in class. So how do you know whether you need to use derivatives or antiderivatives or just kinematic equations? You can always use derivatives and antiderivatives unless you're solving for t, and then it's really kind of tricky. If your x, v, or a is a function of time, so in other words, you see t squareds and t cubes and stuff in there, then you need to use calculus. So derivatives and antiderivatives, absolutely. If you have a falling object without air resistance, a is constant. It's 9.8 meters per second squared, so you can use the kinematic equations. And if a is given as a constant value, like 5 meters per second squared, or the problem says it's constant, then you can use kinematic equations. So really, what tips you off that you need to use calculus is that there's like t squareds and stuff in the equations that you have. So if you don't see that, you probably don't need calculus.